My name is Mayank Shah, and today I'm going to present my seminar on the topic a brain-inspired low-dimensional computing classifier for inference on tiny devices. Now, the seminar is being presented on the work done by Shijin Dua, Xiaoluen Zhu, and Xiaolei Ren. So this is the presentation as part of the EE514 course, and we shall move further in this seminar. So the table of contents or the flow of the presentation that we will be following is as such. We'll start with the introduction, then followed with the basic hyperdimensional computing, what it really means, the brain-inspired HDC classifier, how they have come into train and what they actually mean, design of the LDC classifier, which is the basic model of the paper, how the mapping is done in the LDC classifier, how the training is done, and how the inferences are then done. And then the performance evaluation on basis of how this LDC classifier is better than HDC classifier in terms of the performance as well as the accuracy. So let us start with the concept. Now, as we live in the day of or as we live in the age of computing, we are always surrounded by computers. We have computers all around us, and we have seen a significant rise in the use of computers in day-to-day life in last 10 years or 11 years. Now, in these 11 years or so, we have also seen the advent of GPUs, where the hyper computing intensive scenario is taken into considerations. The advent of deep learning, the advent of implementing learnings into day-to-day scenarios to understand, to make computer understand the environment on its own, have created a lot of computation, and the computational devices had thus come into market. So as the first image shows itself, we can see a GPU system. So a GPU system is normally a server, and we can see that image that it requires a specific criteria, or it requires some specific setup where it has to be installed and then worked upon. Now, when we talk of artificial intelligence as an application, and when we talk of artificial intelligence in a day-to-day life, there are a lot of areas where artificial intelligence or where computer vision would need would be needed to work instantaneously. As in, if we take a scenario of a self-driven car, so as we can see here, now this is a basic hardware of a GPU environment, and this is a basic car. Now if you can see the dimensions of the GPU environment, this car would not be able to accommodate this much processing power in this setup anyways. Plus the heating issues and the entire ergonomics issues of the car would be a very typical, or would be an impossible job to work with. So what happens is that when we work in a self-driven scenarios, that is, our sensor is catching, or our camera is catching the views, and those views need to be processed instantaneously to let the system know that okay, when to put the brakes on, or when to put the brakes off, or when not to put the brakes on. So in such scenarios, we need a computation model which is very fast in order to process that can be work on a real time, or we can even say that the edge devices would be able to compute on its own. We do not need a server or a specific GPU environment to process the information that we have gathered. Similarly, we can see another application, as in, if a person who is a handicapped person, who is not able to walk freely, and who is not able to actually run through the entire wheelchair on his own. So if it's a mechanized wheelchair, it's an automatic wheelchair, your electrodes would be able to give you the brain signals, and the signals would be computationally processed and will give it to your wheelchair. So basically it requires real-time computations, and for real-time computations, going to the GPU powerhouse and going through the and churn the results out of these GPUs, which is not a very good scenario. So in terms of getting the computation in the real environment, the environment HDC was introduced. That stands for hyperdimensional computing. Now hyperdimensional computing, as the name itself suggests, it is when the input streams are defined in terms of hyperdimension, that is, the dimension of the input would be very high. Now, how does it actually works is that when the dimension of the input is very high, and take it to a concept of GPU, or suppose CNN, which is moreover used in a visual scenario. So when we talk of a CNN, even though the input scenario, or even though the input encoding is very weak, the encodings that we generate, or the features that we generate over the convolutions, are very high. So hyperdimensional computing says that most of the computing time that the GPUs put together are used during the convolutions in order to create the features. But hyperdimensional vector says that if the feature vectors are initially at the very single time are available as the input stream, So we may be able to get the processing time down because now there is no computations to be done on feature generation, but rather only a single matching between two vectors is to be done to decide on a conclusion that whether to put brakes on or whether to not put brakes on. So these type of inferences may be drawn from a hypervector by simply a difference calculation in between two devices. But now as a term hypervector in itself suggests that the input is very heavy, input is very high on dimensions. So it will take a lot of memory and it will take a lot of computing power to actually process this also. Now traditional computers, traditional von Neumann computers would not be able to do it, but the recent advent of in-cache processing and the recent in-memory computing would help us in this scenario. But still, we would still require a hyper-dimensional processor in order to process this hyper-dimensional computing. So these are some drawbacks that any hyper-dimensional computing would refer to. So wouldn't it be a much prefer way that we can utilize the feasibility of hyperdimension and we can calculate it in a much easier way? But that is, we can use a low dimensional computing in a scenario of hyperdimensional. So we may basically optimize the input streams such that the processing power is not compensated or the processing power is not hampered in the scenario. Now, let me give you an idea that what is the basic idea of hyperdimensional computing classifier, and then we will be able to identify that, okay, how low dimensional classifier would actually work upon. So the HDC basically generates value and hypervectors. So when we talk of an HDC, there are four type of vectors that are generally taken care of. Out of these four vectors, two vectors are moreover used. That is your feature vector and the value vector. Now, feature vector is the first vector that we create because we are what we try to do. As the introduction itself I said that in convolutions we generate features and then we populate the features. Here we are saying that in a single vector the features that we have, the most of the features that we can be generated are generated and these are kept into the vector. So this vector would be called as a feature vector. Now there would be required some value to this feature vector in order to identify the scenarios. We can also look this into in terms of it is a type of attention, that how much attention we are trying to give to the feature vector. So value vector can be synonymously, or value vector can be actually referred to as the attention of the feature that is required. So first we generate the feature vector and hypervectors, which would be the input. Then we encode them as in that how these vectors would be generated and how these vectors would give us the final output. So the encoding is done is as an input sample is encoded in a sample hypervector by fetching the pre-generated value. So this pre-generated value basically would be an attention that we are talking about and hyperdimensional vectors from the item memory. So we will talk of this in the architecture, and this encoding is basically but nothing but a Hammadath product that happens on these two vectors. That will be if f is your feature vector and v is the hypervector, then encoding would be nothing but f transpose into h. So this would be the encoding. Then it goes through the training process. If there are k classes and if there are f features, so these f features would be somehow trained into these k classes overall. Okay. The training mechanism is generally we take the, if there are suppose n vectors in a specific class, then we take the average of these n vectors and we say that now this vector would be the class hypervector that has been generated. Now if there are, when you talk of inferences, now whatever the training data, testing data we have, now we have created a class vector, and the class vector is nothing but the average of all the vectors that belong to a same class. Now all we have to do is we have to compute the difference, or we have to compute the distance between the input vector with the corresponding vector, and we'll be able to get the output. So this is how a general HDC classifier works. Now this is the basic architecture we can see. So if you take input feature is nothing but your feature vector. Now feature vector would be here base 1, base 2, everything is the value vector, and we then basically multiply or we create a feature into value vector out here. So that is your HD base. Now in terms of your encoding, when everything here is done, then you go for training. Training is nothing but you define the k classes and you average the inputs as such here, and then you file it into the associative memory, which will actually give you class 1, class 2, class k, these are your k classes, and all we have to do is we have to now check the testing fixture with the distance that we get from these scenarios. So this is how a basic hyperdimensional computing actually works. Now the only disadvantage of this hyperdimensional computing is the size of the input vector that we have. So we are saying that it's a hyperdimensional, that the dimension of the input is very high. So how do we actually control it? How do you actually work on it? So that is why the writers of the paper propose a design of LDC classifiers. Now what this LDC classifier means, LDC classifier in itself is a low dimensional computing classifier. So low dimensional computing means it works like a hyperdimensional, but instead of a hyperdimension, it reduces the size of the input dimension. That is why it is saying low dimension. So the process of this would be, the initial part is we first mapping to a neural network. We first map to a neural network. Once the mapping to the neural network is done, then we do the element. Then inside the mapping of neural network, we have encoding, we have value mapping, we have element wise binding. Then similarity checking would be done, end-to-end mapping would be done, and training the LDC classifier and inferences. So all these things would be the basic would define the basic model of LDC classifier. Now let us proceed that how it goes. So as the process said, that encoding, now encoding is the process when we are defining our hypervectors, when we are defining our low dimensional vectors. So how do we generate? So first of all, we have a feature box. This is the feature that we have. So feature, whatever number of features we have, this feature is of a low dimension, as we have suggested right now. It is a low dimensional feature that we have. Now a value box is there. This value box corresponds to a value function or a value corresponding to this feature, now suppose, how does this actually happens is that this value box is nothing but a neural network where we generate the value from this feature vector. So if we have an n dimensional feature vector, we will get one, or we have value associated with this feature vector using this encoding. Now this encoding will then be element wise binded. So element wise binded means that if there are n vectors, n value features, and there are n features, so these will be binded together, means it will be a Hammadath product, and these Hammadath products will give us specific signals, or specific that is delta 1, delta 2, delta f. These are the encoded form of the input. So we have encoded our vector into these vector size. Basically our feature vector has now been encoded into this vector. Now after the encoding is done, we do the similarity checking. Now how does similarity checking works? So similarity checking, as you can see, this takes in as S is basically your input features that we have generated after encoding, and C is a matrix, or C is a value matrix that is there. So what value matrix basically is, so C1, C2, and so on. So this is a K when we have K classes in the setup, and when we have D features. So this is a D cross K matrix that we have. Now this D cross K matrix, what it really does is it will calculate the similarity between the features that we have. So similarity between the feature amongst with the this classes that we have. So this is the similarity checking. Once the similarity checking is complete, we create an end-to-end mapper. End-to-end mapper means that we combine all these three fundamentals together. So your feature vector is feature 1 to feature n. It goes to a value mapper. It gives you a value function. This value function is then taken through the scenarios, and you get a complete feature vector, that is S. This S is taken to a class layer, and this class layer will give you a matrix, or give you a similarity index, that how similar are these vectors together. Now when we talk of training the LDC classifier, because we are using a neural network as an index, so it uses an Adam optimizer. The loss function is cross entropy. So the value vectors we can be extracted from the value box recording. We have already seen this, that what value vector v means. Feature vectors are extracted from the weight matrix in the feature vector, and the class vector C can directly extract it from the weight matrix in class layer. Now this is the class layer and this is the weight class matrix that we are talking about. This is what C basically is. Now once we've defined all the similarity checkings, we are only left with inferences to take care of. Now what this actually means is that we have created a matrix which gives us that okay, this feature is similar to this class and this is the value of the similarity. Now all we have to do is we have to just simply target, or we have to just simply check the query and check with which class and with which class the distance of the query is minimum. The minimum distance of the query would be taken as a class for the specific feature, and this is how an LDC classifier actually works. So LDC classifier basically takes the methodology of the HDC classifier of mapping, encoding, similarity checking, and values, but it works on a low dimensional feature vectors, which actually increases the processing power, but it also takes care of the edge computing scenario as well. So as part of the performance evaluation of the setup, the LDC classifier has been uploaded or has been checked with MNIST dataset, Fashion MNIST dataset. These two are available in TensorFlow. Then there are this CTG is a cardiograph dataset that has been used, and this UCHAR and isolate are basically real-time datasets that are available for real-time interactions. So the number of parameters, the train test classes, the distribution, everything, these are the configuration of the LDC that was used. Now once these were used, there are the MNIST and CTG, the hardware acceleration can be seen here. So on MNIST, the LDC classifier actually got 92.72% and HDC got 87.38. So it is, we can see that there is a marginal update up, marginal improvement in the accuracy that we got using LDC classifier. Similarly, even in the CTG, that is your cardiograph data set, we get an the writers get an LDC, the writers get an accuracy of 90.50 on source HDC also. So this is basically the hardware, this is basically the inference accuracy and everything that the writers were able to achieve. So as part, so this is basically this we can say that LDC is basically an improvement to the HDC classifiers. Yes, there are certain points which still are working upon that. How do we actually recognize the optimal size of the input vector? So that is an open area to discuss still, that because hypervector, the hypervector is basically keeping a charge of every single feature that we have, and when we creating a feature value vector, we are generating it from a neural network. So that part still, that what would be the optimum size of the vector, that is still up for discussions, but still the writers were able to actually identify these many advantages of the scenarios. Now the references used for the presentation was the base paper was Dia Shijin and Zhu, that was printed in 22 March, and the HDC classifier or the information of regarding HDC is basically taken from the paper written by Hassan, Iman and Halawani. So this was also published in about 2021, so a recent paper that is. So that would be all from my end. Thank you.